second lab of the year. The last one was to study constant motion or uniform motion. We found the velocity of this smart cart as it was moving at a constant velocity. We found that by taking the slope of a position time graph. Today what we want to do is find the acceleration of a smart cart as it's on an incline. Now, I'm not going to give you the problem. Okay? I've almost given you the problem already. But remember, the problem is always phrased in the form of a question. So we're trying to find the acceleration of a smart cart today. That's what we're doing. We're trying to find the acceleration of the smart cart today. You turn that into a problem. Okay? Now, last time you didn't have to do variables. This time you do. So I'll briefly explain this as a review from previous years. You remember that there's always one manipulated variable in an experiment. This is no exception, one manipulated variable. Now, we always think of that manipulated variable, or we usually think of that manipulated variable, as the variable that you change. That's not always the case. The manipulated variable is the variable that causes something else to change. That's often something that we change that causes something else to change, but not always. In this case, as in the last lab that we did, if we had to figure out the variables, it would have been the same thing. In the end, there's something here that causes something else to change. Does that make sense? Something here that causes something else to change. Now, if you pay really close attention later on, you should be able to figure that out just by logic as I show you what graphs to plot. Because you know where variables appear on graphs, right? So if I tell you plot this graph, you should be able to figure out from the graph what variable is the manipulated variable. And on the same token, you should be able to figure out which variable is the responding variable, the one that responds to the manipulated variable. So one variable will cause a change. Another variable will be changed because of that. And then control variables, well, there's an infinite number of control variables, right? It's everything else that needs to remain the same. I don't expect you to list 30 control variables. I expect you to list anything that's important, like important control variables, okay? There's usually one or two important control variables here. In this one, there's really one critical control variable here, and we need to see the one critical control variable. If you list something like, well, we need to keep the temperature the same throughout the experiment, technically we should, right? Keep the temperature the same and the humidity the same and so on. But is that really going to make a difference? Like, not really, not any measurable difference, right? If you put that, it's not going to get marked wrong, okay? But I'm looking for more than that. I'm looking for something that hopefully should be fairly obvious to you, okay? One, that if you change this, everything changes. The acceleration, which is what we're looking to find, changes. Got it? So one critical control variable there. Now the apparatus is going to be almost exactly the same as we used last time. You're going to use your phone with the Sparkvue app, which is going to be connected to a smart cart, which is going to be on a track. Difference here is we don't have these white ones connected to each other. Okay, we have these white ones separated this time because you're going to put them on a ramp, or you're going to put them on a little a box or a book or something to create a little bit of an incline. So the only difference in the apparatus for this is that you're going to have a book or the box or something to create that incline. That's what's going to cause the acceleration. Does that make sense? So you put your smart car on the ramp. Set it up, turn it on, right? Make sure that you're in the right spot on your app and so on. And because that ramp is elevated at one end, when you let it go, it should start speeding up when it goes toward the other end. Good? Now, the app, this should look familiar to you. The app, you're only going to want to connect one smart car, right? Red one, blue one, doesn't really matter. In this picture, I've actually got two smart carts connected. We only want one connected. And you want to make sure that it's yours that's connected, because you might have 3 or 4 of them pop up. Make sure that the number is yours, just like last time. Now, last time I asked you to select this position, right? And this table and graph. This time, what I want you to select is velocity and table and graph. That's not going to make any difference in terms of the actual data that you're going to collect, but it is going to make a difference in terms of what you're going to see on your screen. You'll still collect the exact same data as you collected last time, different numbers of course, but the same variables as you collected last time, but it's going to be easier to see if you have good data, if you select velocity and this one. Does that make sense? So don't select position, select velocity and that one. And there's not going to be smart card number 2 down below because you've only got one of them connected. Now, what is the procedure going to look like? You're going to need to do the procedure for this. You haven't had to do one yet. I'm not going to give you the procedure in words, but I'm going to give you the expectations of a procedure. The general expectation is this. If I taught another Physics 20 class after lunch, you should provide enough detail for that Physics 20 class to perform the lab. Got it? Now, that doesn't mean that you have to explain how to use the Sparkvue app, because they know how to use the Sparkvue app, right? They've used it before. That doesn't mean that if you break your pencil lead when you're collecting data and you went to sharpen it, that you have to say in your procedure that you sharpened your pencil lead. Okay? They don't need that information to perform this lab, right? What information would they have needed to perform the last lab, the constant velocity lab? What would we say for step number 1 for that last lab? Well, even before we connect anything, you got to collect your materials, right? Now, you've listed materials already. Okay, you've listed the materials already, so you don't need to repeat that. You don't have to say collect the phone, the track, the whatever, right? Say collect materials if you've already listed materials. Collect the materials. For the last lab, you would have said for step number 2, place track on a level spot on the floor. Place track on a level spot on the floor. That's not going to be the case this time, right? Because it's not going to be on a level spot on the floor. It's going to be on an incline. But in the last one, step 2 would have been place the track on a level spot on the floor. Step 3 would have been place the card on the track at one end of the track, right? Step 4 would have been using the Sparkvue app, press start on the Sparkvue app, then give the card a push. You don't have to push it this time because it's going to be on an incline, right? Just let it go. Press start, give it a push. What's the next step? Stop it, but before I even stop it, I'd probably press stop on the Sparkvue app, right? That's part of the procedure. If somebody doesn't say press stop, then you're still collecting data. When did we do that lab? Like a week and a half ago? A week ago? You're still collecting data if you never press stop on that, right? So you got to press stop. And then you might want to say, like, put your foot in the way to stop the card at the end of it, or whatever the case may be, which you're also going to do today, by the way, because I don't want it going onto the floor. Okay. It's a pretty straightforward procedure. So is this one, a pretty straightforward procedure. In fact, it's an awful lot like last week's procedure, except that it's not on a flat horizontal surface, it's on an incline. Do you see the kind of detail that we require for procedure? You don't need to go further and say plot a graph, blah, blah, blah. That's analysis. You don't need to tell me that stuff. That's not part of the procedure. Okay? You want to write down what another class would have to do to collect data. Not after that, not before that. Not details like, stubbed my toe on a desk, so I moved the desk out of the way, then I dropped my pencil, and then I picked it up. You don't need to put details like this, right? What details would be needed for another class to perform this lab completely and well? Okay? That's your procedure. And by the way, we list those steps in the procedure, right? We don't just write it as a paragraph. We list those steps. Step 1, step 2, step 3. It's not dash, dash, dash. It's step 1, step 2, step 3, however many steps. And by the way, if you combine a couple, like Martin has 5 steps and Marcos has 6 steps, as long as they both say essentially the same thing, that's okay, right? Like, we're not counting steps here. We're just looking at whether it's complete or not, okay? Your table, when you import it into Google Sheets, okay, it's going to have a lot more detail than this, right? Just like last time. What are you going to do? Delete a whole bunch of columns, right? But last time you kept 2 columns. time and position. Notice this time you're keeping 3 columns, time, position, and velocity. If you have 4 trials, that's fine. You only need 1. Pick the trial you want to use and delete all the other data. You should have a total of 3 columns, time, position, and velocity. You got that? Now, if you forget how to import that into Google Sheets and so on, okay, I can help you with that. There's also instructions on Google Classroom for that. Remember though, as somebody, whoever is using their phone to collect the data, puts it on their own Google Drive, shares it, what do you got to do before you actually start plotting graphs or before you start deleting columns? Make your own copy, including the person that shares it needs to make their own copy. Nobody works off of the original document. You share it, the original document, and then everybody makes a copy and works off of the copy. Now, there's our data table. It is data because we haven't done anything with it yet, right? We've just collected our data. Our analysis this time isn't going to have any analysis questions, but it's 2 graphs. The first graph that you're going to plot here is position and time. Don't forget to put units in. Don't forget to put a title in, and so on. Okay, that position time graph is going to have data points, or it should have data points that looks something like this. It's accelerating, right? So we would expect a position time graph that looks something like this. You do need to add a trend line for this. That trend line will not be a linear trend line. There's different options. I want you to pick, try them all. See which one fits the best. Got it? So add a trend line electronically and pick the one that fits the best. You should find one that fits very well and almost connects the dots. You do not need an equation for this one. You do not need to display an equation for this one. All right? Next one, this one's going to be velocity versus time. This one should be pretty close to a straight line. That one also requires a trend line. But this one also requires the equation. Now, somebody said last time, when I showed you the graphs, the equation appeared at the top. And somebody came to me last time and said, well, I can't get the equation appearing at the top. It's appearing at the side for me. I'm not sure why it appears at the side sometimes and why it appears at the top sometimes. But does it make a difference? Not really. No, not really, as long as the equation's there, right? Make sense? Now, your problem was, well, basically you wanted to find the velocity of the car, right? Or sorry, not the velocity, but the acceleration of the car as it went down the incline. Although that's going to be phrased in the form of a question. Your conclusion will be, answer that question. Okay, whatever your question was, answer it. Okay, so you got 2 sentences. One sentence is the answer to the question. And then the second sentence will be to justify it. So how do you know that's the answer to the question? If you're looking to find the velocity and you phrase that somehow in the form of a question and you gave me the velocity there, it's like, well, how do you know it's the velocity? Just tell me in one sentence where it came from. How do you know that the velocity, sorry, the acceleration, I should say, I keep saying the velocity from the last lab. How do you know that the acceleration is 0.95 meters per second squared, or whatever the case may be? What should you expect? Like, we don't know what the acceleration is going to be, right? In fact, it's going to be different for different groups depending upon the slope of your incline, right? But what should you expect it to be less than? What should it not, in any circumstances, be bigger than? There's an upper limit that it cannot exceed. If I keep making my slope, my incline, bigger and bigger and bigger, the acceleration will get bigger and bigger and bigger, right? The steeper it is, the more it's going to accelerate, right? What's the maximum rate that it'll ever accelerate as it goes down that incline? Somebody started saying that, I think. Yeah, 9.81. Because when it becomes vertical, it's just going to free fall, right? At 9.81. Clearly, you're not having your track vertical, right? So it will be less than 9.81 meters per second squared. It should be a lot less. It should be a lot less than 9.81 meters per second squared. I don't want you to have anywhere close to a slope that would give you remotely close to that value. Now, you might have to perform a couple trials here, right? Like, we only technically need one trial, but if you do it the first time and it's like, oh, it barely moved on that, what do? Do it again, but make the slope a little bit steeper. I would say to you, please start with a small slope. If you're erring on the side of not getting great data, then err on the side of not accelerating enough. We don't want to make it too big of a slope and then have this $300 car crashing at the bottom. Okay? You don't need that much of a slope. Just start with a small one, and if you have to go up a little bit, go up a little bit. If you don't, then you don't. And then, of course, your sources of error. We need 2 or 3 good sources of error, and then we need suggestions for improvement. Remember to avoid human error, right? You know, like I accidentally kicked the track out of the way. Well, don't do that, because that's your fault, right? We want to do something we want to express things that aren't your fault. They're errors, but aren't your fault. Now, I didn't say this before the last one, but a couple of people came to me about issues like this with sources of error. Like, if you find a source of error partway through and you fix it while you're doing the lab, that still counts. You can still use that as a source of error. And your suggestion for improvement is actually not a suggestion for improvement. It's an improvement that you already did, right? That's okay. In fact, it's better to fix it now than it is to fix it next time, right? So you don't not fix something because you want to save it for a source of error. Fix it and still use it for a source of error. Make sense? Remember, those sources of error relate to apparatus, procedure, issues with time management, right? Like with class issues and so on. Okay.